Hi there. In this clip, I will talk about exceptions to the octet rule and how you can master them. The basic approach shown in my former clip remains the same, but I have to say that most of the structures you will have to work on are exceptions, since only carbon, nitrogen, oxygen, and fluorine always follow the octet rule. In the following, I will show you how to deal with electron-deficient species and hypervalent structures. If you're interested in radicals, I invite you to watch my clip on that topic. Elements with an odd number of valence electrons often have no possibility to acquire an octet. They give rise to electron-deficient molecules. Especially the elements of main group 3 in the PSE are known for that. But also other elements with odd number of electrons can give rise to electron-deficient molecules. A typical example is borane, BH3. We draw the skeleton molecule with borane in the center and group the 3 hydrogens around. We assign the valence electrons, 3 for boron, 1 for each hydrogen, and substituting bonding electrons by lines, we obtain the final structure like this. Drawing main group 3 element halides is not as straightforward. In fact, several structures may be envisaged, like this one, where the fluorine atoms alternately form a double bond with boron. However, these resonance structures are not valid since boron would have a negative formal charge. More on this topic will be treated in another clip. Another possibility would be that fluorine grabs one of the valence electrons of boron, leading to an ionic structure. However, there is no experimental evidence for that. Thus, after developing the Lewis structure as usual, we end up with this structure, and after drawing lines for the bonding electron pairs, we see clearly that the fluorines feature octets where boron remains electron deficient with only 6 bonding electrons. Before I talk about hypervalent species, let me give you an idea where you can find the elements giving rise to hypervalent structures. In the periodic system of elements, you will have them lower than period 3 and especially on the right-hand side of the periodic system as indicated. In this section, I will treat hypervalent structures. To start with, I would like you to focus on the sulfuric acid anion. Counting electrons around sulfur, we end up with 12. How can this be? Drawing the Lewis structure as usual, with sulfur as the least electronegative element in the center, we count a total of 30 electrons, 6 from sulfur and 4 times 6 for oxygen. But the total is 32 electrons since we have to count the 2 negative charges. These 2 negative charges may be inserted like this, and everything looks okay, with octets around each atom. But calculating formal charges with the help of this equation, where Fc equals number of valence electrons minus number of non-bonding electrons minus number of bonding electrons divided by 2. I have a review clip for that, which provides more details and examples on this topic. We obtain for the proposed structure of the sulfate ion a formal charge for oxygen of -1, which we assign to each oxygen, and for sulfur, we obtain a +2. But in a molecule, formal charges for each atom are required to be as close to 0 as possible. Thus, we will have to look for a better structure which we may obtain when rearranging electrons in this way, pulling 1 electron pair of each of the 2 oxygen atoms as shown, and place them between sulfur and oxygen. Drawing lines for the bonding and non-bonding electron pairs, we obtain this structure with 2 double and 2 single bonds. Calculating formal charges gives us the following results. For the 2 oxygens, which are double bonded, we obtain a clear 0. For the single bonded, we obtain a -1, which is okay since they bear a negative charge. For sulfur, we obtain equally a 0. We can't probably get closer to the requirements for formal charge counting, so we can trust that this structure, not considering resonance, is correct. My last example is chlorous acid. As its sodium salt, it's used in commercial bleach. We draw the Lewis structure as usual, with chlorine as a less electronegative element in the center. We flank it with 2 oxygens and we put hydrogen on top of it. We assign the valence electrons, 7 for chlorine, 6 for each of the oxygens, and 1 contributes hydrogen. There are 20 valence electrons in total. Substituting electron pairs by lines, we obtain this structure, which obviously satisfies the octet rule. Formal charge calculation gives us what result? We get for hydrogen 0. For oxygen, we obtain a -1, and for chlorine, a +2. These non-zero charges indicate that there may be better solutions for this molecule. Like this one, with hydrogen still bonded to chlorine, which as before features a lone electron pair. The oxygens are now double bonded to chlorine. Another possibility is that one, with only 1 oxygen double bonded, hydrogen is moved to the now single bonded oxygen, and chlorine has 2 lone electron pairs. Also here, the structures both look okay. What does the formal charge calculation give? We have, for hydrogen, in each case, 0. For the double bonded oxygens, we obtain 0 again. For the single bonded oxygen, 0 again. For the chlorine in the left molecule, 0. And in the right molecule, equally 0. What to do in this case? The solution is to choose the structure with the smallest number of bonds, which means the molecule upright. This last slide is not fundamentally necessary for you. However, I want to highlight the question whether hypervalency occurs due to the participation of d orbitals, as many teachers maintain. With the examples of phosphorus pentafluoride, I want to discuss this. The shape of the molecule is trigonal bipyramidal, and the following resonance structures are proposed. Considering the 2 axial fluorines, they are thought to alternately take up the negative charge, giving rise to 2 resonance structures. Then, the 3 equatorial fluorines are supposed to do alike. In both sets, phosphorus remains positively charged. A mix of these 5 resonance structures reveals that phosphorus always takes a positive charge, whereas the negative charge is distributed over the 5 fluorines. Following this reasoning, short-lived ionic states of the molecule are responsible for hypervalency and not d orbital participation. Research confirming this has been done as early as 1969 and latest in 1990. Thanks for watching. See you again.